Hello and welcome to part 2 of this example problem. In part 1, which I would suggest watching before watching this video, we took a look at a continuously stirred tank reactor problem in which we are solving for the concentration of A, our substance, with respect to time, and the the temperature of our contents within the reactor with respect to time. So I've gone ahead here and imported our numerical Python, our tools for plotting, and I've gone ahead and also entered in our parameters which we have been given for this problem. So we have Q here, our volumetric flow rate. We have Ca in, which is the concentration of A going into the tank. We have the temperature of our contents going into the tank, which is T in. We have our V here for volume, which is constant. We have the density, which is actually for water. We have our heat capacity, C. And this HR term here is the enthalpy for the reaction that takes place, so HR. This ER term here is the activation energy divided by R, the ideal gas constant, which will be used in solving for K, the Arrhenius equation. And this K naught here is the coefficient here in the Arrhenius equation, which we have been given, which will again help us solve for K, which is needed for our right-hand side that we will be solving for, or actually both of the right-hand sides that we'll be solving for. This UA here, if you'll remember, is the transfer of heat within or between our reactor and the coolant times the area, so UA. And down here, lastly, we have our three initial conditions. So the temperature of the coolant initially, the concentration of A initially, and the temperature of our contents initially. So what we need to do here is go ahead and define our right-hand side function here. So go ahead and define our right-hand side, and what we will need to do here is first we will need to supply our independent variable, which will be time. So right-hand side, and we will need to supply time, and second we will need to supply a vector of our dependent variables, what we're solving for. So we'll have just a dummy variable here, so vector, and we can go ahead and unpack that vector into what we're solving for. So we're solving for the concentration of A and the temperature of our contents, so that'll be equal to vector, just unpacking the vec term. So next here, since like I mentioned before, we need to solve the Arrhenius equation for K, since that is needed in our right-hand side expressions, we can go ahead and do that here. So K is equal to K naught times the exponential of negative E divided by R, which is this term here, and that is divided by the temperature. So we'll have NP dot exponential, and we'll have negative ER, capital R, and divided by the temperature, T. Okay, so now we can go ahead and return our two expressions, our two right-hand side equations that will allow us to solve for the change of concentration of A and change of temperature. So we will do return, and since we have unpacked the concentration of A portion first, we will have to supply that right-hand side first in our return here. So if you remember, this is Q divided by V. This is multiplied by Ca in minus Ca, so the concentration of A going in minus the concentration of A leaving, minus our reaction here. So it's K times the concentration of A, so K times Ca. Okay, and that is our first right-hand side, and I believe I have parentheses matched up. Yep, we look good. Okay, so our second right-hand side, solving for the temperature of our contents here, will be Q divided by V, and this will be multiplied by our temperature going into the reactor minus the temperature of our contents. And from here we will add the enthalpy of reaction, so HR. This will be multiplied by Ca, and also be multiplied by K, the Arrhenius, or what we solve for right here, the Arrhenius equation here. Okay, this will be divided by the density times the heat capacity C. So again here, I'm just inputting the right-hand side of what we have solved for in part 1. So if none of this makes sense here, I would suggest going ahead and watching part 1 of this video. So we'll have density times the heat capacity C. And from here, we will have to subtract that heat transfer term that we solved for here. So I have UA, and this will be multiplied by T minus TC, so the temperature of our contents minus the temperature of the coolant. And this will be divided by density times, we'll write it out here, density times V, and this will be multiplied, I'm trying to remember here, this is multiplied, let's see here, we have that parentheses match up, yep. Okay, so we're good. Okay, so density times volume times C, okay? So we have those matched up here. Our parentheses do look good, so hopefully we don't have an issue when we actually go to solve this. But one thing you will notice here is this TC term here. We don't know TC. However, again, in part 1 of this video, we actually read what this problem wants us to do. It wants us to go from a steady state of our coolant temperature of 300 kelvins and do two different scenarios. So take steady state 300 kelvins of our coolant down to 290 kelvins for our coolant and see how that affects the reactor, and also take our steady state 300 kelvins for our coolant and raise it to 305 kelvins. So first, we can do the first scenario. So we'll set TC equal to 290 kelvins here. So I'll go ahead and comment this out as kelvins so we know what that is. So I'll run that here, and now we know TC. So hopefully I don't have any issues there. My parentheses, I think, look good. So next here, what we'll need to do is actually use solve IVP to solve our right-hand side here. So we'll have solve IVP, and we'll need to supply our right-hand side here first, and second, we will be supplying our simulation period. So this will be 0 to t end. I'll set that as a variable, and to start here, and we can change this throughout our simulation to see different simulation periods, but I'll just set it to 100 first. Okay, and next here we will need to supply our initial conditions. So we have our CA naught and the temperature of our contents initially. Okay, so after this we will need our method, and we will be using the Raoul integration method. I'm not going to go too in depth on it, but that is the method we will be using in Python here. So Raoul, okay, and we will have our dense output here. So dense output will be true. And that should wrap up this here. Okay, so let's go ahead and run this and see if we didn't make any errors when typing this code in here. Okay, so it looks like we have one error. Let's see what it says here. Float is not callable. Alright, so I went ahead and found the issue here. It was just a simple typo. I forgot to put the multiply sign here. Whoops. Actually did that, but I forgot to put the multiply sign here between these two terms here. So hopefully when we run this, should be good. Okay, yep, that's what we want. Okay, so from here what we can do is we can go ahead and grab this solution here. So if we do dot solution, and we'll actually go ahead and set this equal to a variable named solution, just so we know that this is our solution. Okay, so I'll go ahead and press Shift Enter there. Okay, so now we can go ahead and plot a simulation here. So we'll have two different plots here for the concentration of A. So we'll see that change with respect to time when we enter in or change our steady state coolant temperature from 300 to 290. And we will also plot our temperature of the contents and see how that changes when we make that change as well. Okay, so the first thing that we need to do here in order to make plots for our simulation is to set up a dummy variable here that will just allow us to linearly space out our points on a plot. So if we just create a dummy variable, tplot, and set this equal to np.linspace, again, which will linearly space out our points, we'll start from 0 and go to tend, and we'll go ahead and plot 500. And after this, let's go ahead and look at our solution here, just to see how it gives us our values here for Ca and our temperature. So if we look here, we notice that we have two different sets of values here. The first one here looks to be the concentration of A, and the second one that it provides is the temperature here. So let's go ahead and unpack this here. So that we're not confusing the two when we go ahead and make a plot for them. So we'll go ahead here and set this equal to Ca and temperature of our contents. Okay, so unpack that. We'll press Shift Enter there. Okay, so now what we need to do is we can go ahead and do fig equal make subplots. So fig make subplots. And what we'll do here is we'll make plots here with two columns and just one row so that they align side by side. So it's just sort of a visual trick here so we can get both of our plots, one for the concentration of A changing and one for the temperature of our contents changing. So if we set the columns equal to 2 here and the rows equal to 1, that will allow us to do that. So after this, we will need to add two scatter plots, one for the to look at the concentration of A and see how it changes, and one to look at the temperature of our contents and see how it changes. So if we do fig.add underscore scatter, our x values here will be our tplot dummy variable. Our y values here will first do the concentration of A. The mode here will be equal to lines, and we'll set this to be the first row and the first column. Okay, and I'm going to go ahead and just copy this down because all we need to change is make this our y value the temperature of our contents and set this to the second column. Okay, so looks like we're good here. Let's go ahead and plot it and see if it works out. Okay, so there we are. So what I'm going to do here, just to get a cleaner look, I'm actually going to change our ending value here down to 10, just so we can look more closely at what's going on here. Okay, so for our first scenario here, when we drop the steady state here for our the temperature of our coolant from 300 Kelvin. If you remember at the beginning of this problem, we had two different scenarios. We're dropping the steady state coolant temperature from 300 to 290 and seeing how the concentration of A and the temperature of our contents respond. And we'll also have a scenario where we raise the coolant temperature for whatever reason to 305 Kelvin and see how that affects it. So here, our first one, we have the coolant temperature at 290 Kelvin. And we notice here that for our second plot here, this is the temperature of our contents here. And this makes sense here. If our coolant temperature gets cooler by 10 Kelvin, the temperature of our contents inside the reactor will drop. And over here, if we see the concentration of A here, this makes sense as well because if we have a cooler reaction, there's less reaction. So the concentration of A will ultimately be higher and higher because you keep adding in 1 mole of A, and since it's at a cooler temperature, you're not having as much reaction, so you're going to end up with a larger amount of A coming out of the reactor. So let's look at this second scenario here. If we for whatever reason change from a coolant temperature of 300 Kelvin and go up actually to 305 Kelvin. And this looks a little bit different, but if we look at it here, It looks kind of crazy at first, but it does make sense. So if we have the coolant temperature raise to 305 Kelvin, we'll notice here that the temperature of our contents obviously will raise, okay? Now, if we look over here at the same spot on the graph to the concentration of A, we'll see that since the reactor is raising in temperature, that more A is being consumed. However, our rate equation, R equals K times the concentration of A, we'll see that if we go down here all the way to 0 for the concentration of A, there's no more A to be reacted. So that's when we'll see a decline here in the temperature of our reaction, since there's nothing left to consume. And you'll see here this oscillates back and forth because we're constantly adding in the same amount of A, the same amount of A, the same amount of A. So we get this sort of oscillation here. And if we look at different temperatures here, like if we go down to 304, we'll look at this here. Okay, so I'm having a little bit of trouble loading this here, it looks like. So it might load here in a second, but if we go down to 304, we may see, yeah, runtime disconnected here. But if we went down to 304 here, what we'll see is that the oscillations may get smaller and smaller, but it's still not really a scenario we want to be messing around with an exothermic process to have these oscillations in a very, very unsteady state like this. Okay, so here, I've gone ahead and it's loaded here. So you can see we have an oscillation here, and if we extend this out, we can look a little bit farther to see how that runs. So yeah, you see the oscillations here. But yeah, so that shows a simulation here for our two different scenarios. So we have changed the coolant temperature to 290 Kelvin, so we've actually cooled it down, and we're able to see what that does to the concentration of A and the temperature of our reactor, the contents in the reactor, and we've also raised that to 305, see what that does to the concentration of A and the temperature of our contents. So that will wrap up this video and this example problem. Thank you for watching.